Hi, I'm Adam Lifshitz, and this is my presentation for Principles of Security Engineering as part of my personal challenge project on passwords and an overview of password security. Let's start with what a password is. A password is a private or protected string of letters, numbers, and special characters used to authenticate an identity or to authorize access to data. It's one of the 5 factors of authentication. We have the possession factor, something you have, like a token or a smart card. The inheritance factor, something you are. That's, for instance, biometrics, such as a fingerprint or a retina scan. The behavior factor, something you do. The location factor, somewhere you are. And the knowledge factor, where passwords fall, something you know or a secret that you know. When we look at the history of passwords, they have their origins in the military of ancient civilizations. Their passwords were a way to exclude undesirables from controlled areas or distinguish friend from foe. The modern computer password can trace its origins back to Francis Cabato at MIT in the 1960s. They used passwords to give users of the compatible time-sharing system access to the system and their files. So not long after the system started in 1962, we had the first instance of modern computer password theft, when one of the users found a way to print a punch card with all the users' passwords and use that to give himself more time and access to the system. Now, passwords have 2 essential elements that make up their strength and make them difficult to crack, and those elements come from their length and their complexity. So length just talks about the number of characters in a password, and complexity talks about a number of different things. So character length, the generally complexity rules are 8 is the minimum number of characters. So a password with 8 characters using only lowercase has 26 to the power of 8 different passwords that can be done. If we add more complexity by adding uppercase and lowercase, then we have 52 to the power of 8 options for that password. If we add numbers, 0 through 9, another 10 characters there, we now have 62 to the power 8 different options for that password. And if we add, let's say, 7 more non-alphanumeric characters, as we have in the example here, we then get 69 to the power of 8 different passwords. So you can see how adding complexity will add to the number of options and add to the strength of a password. Again, password length is the same. If we then take this 8-character password and make it a 12-character password, then becomes 69 to the power of 12 number of different passwords that can be made. So there are pros and cons to complexity. Obviously, the longer and more complex it is, the more work and time is required to crack a password. But unfortunately, passwords are used by humans. And for humans, complex passwords are hard to remember. And when humans have to remember a lot of complex passwords, they default into more simple passwords. So they will use commonly used words, such as the word password, a name, their own name, the name of the company they work for. In some cases, just a string of numbers, 1, 2, 3, 4, 5, 6. People will also do something called let's speak, where they replace the letters in a common word, such as password. They'll replace the O with the 0, they'll replace the A with the @ symbol, or they'll resort to something called root passwords, where they'll take a common word, such as password, and they'll add 0, 1 and an exclamation mark after it, and the next iteration of the password will be password 02, and onwards and onwards and onwards. And whilst these passwords meet the complexity requirements, they're still quite simple passwords, and you see when we get to the attack types, it makes it easier for attackers when people do this. So password policy for companies, for organizations, is often guided by different cyber frameworks, and there's a lot of cyber frameworks out there. There's ISO 27001 and ISO 27002. We have the Center for Internet Security, and then we also have NIST, which is the National Institute of Standards and Technology. So in 2020, NIST released an update of their cyber framework, and in particularly document 863B, which looks at passwords. And I think it's important that we look at that because it's a departure from previous best practices, and those previous best practices are still followed by many organizations. So in this latest update, they said length is more important than complexity, and that's a recognition of the issues with complexity for human beings. they changed to not enforcing resets. NIST is saying that the more often you enforce resets, whether it's every month, every 3 months, every 6 months, this will cause people to revert to simpler passwords because they're constantly having to change their password. The other thing was to enable show password. So NIST is saying that the risk of someone stealing a password by looking over someone's shoulder is very, 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 very minimal. So it's better to enable show password, and that way people are less likely to make a mistake and less likely to have to change their password as they've forgotten the password, and therefore less likely to result to simple passwords. They are allowing the use of password managers, and we'll talk about that a bit later in the presentation. It's important that passwords are locked after multiple failed attempts. They're recommending the use of two-factor or multi-factor authentication. They're also advising the removal of password hints. And most importantly, the organizations should monitor new passwords. So whenever someone puts in a new password, that should be monitored against a database or a list of previously compromised passwords, commonly used words, and previously used passwords to avoid some of the pitfalls of passwords. So an organization can store a password in 3 ways: plain text, encrypted, or hashed. Plain text is obviously the most simple way. That's where a user's password is stored in the company's database in its plain text form. So any attacker who gains access to the password database can easily see all the user's passwords. Don't have to do anything, they're right there in front of them. You might think, why are we talking about this? It's crazy. I'm surely no one saves password in plain text anymore. But in 2019, Facebook had to admit to storing hundreds of millions of passwords since 2012 in plain text. The next way to store a password would be to encrypt it. So encryption works in the way that plain text passwords are passed through a reversible encryption algorithm with an encryption key, and then what is outputted is an encrypted ciphertext. And this encrypted ciphertext is what's stored rather than the password itself. So this ciphertext can be passed through the algorithm again with the same encryption key, and it can be decrypted back to the original plaintext password. This process in itself has its own issues. You also have to securely keep your encryption key, and if an attacker gets a hold of the encryption key, then they can go and decrypt any of the passwords using that encryption key. Some of the common encryption algorithms that exist are DES, which is no longer used, but it's important to talk about it as it's a precursor to triple DES and AES. Triple DES, which uses 356 blocks for 168-bit encryption. This is also an older form of encryption, and it's being phased out, but it's still used by a lot of financial institutions, specifically for ATM pins. Then we have AES, which is the Advanced Encryption Standard. So this is the new standard for encryption. It's very secure at 128 bits, but the preference is for 256 bits, and AES can only be broken through brute forcing. And then we have RSA, which is named after its inventors, Rivest, Shamir, and Edelman. This is a very secure algorithm. It works with 2 keys, large prime numbers, and an additional value. And whilst it's highly secure, it's also very slow because of the way it works. So it's not really suitable for encrypting passwords. So if encryption is not the best way to store passwords, what is? Let's look at hashing. So hashing is basically a cryptographic function where you take a password or a string of data of any length and you put it through the hashing function, and it gives you an output of a predetermined length. So you can see in the example on the right, if we took the word fox and put it through our hash function, we would come with a hash sum or an output that's 8 characters long. There's no key, so the result is always the same for the hash function. So if the input is the same, the hash sum will always be the same. So hash sums are one-way functions. You can't reverse a hash function. And you'll see in the longer form of that sentence there in the example, the output is still 8 characters long. And if we make one small change, whether it's one letter or one word within the sentence, put it through the hash function, you can see it has a very drastic change to the hash sum that comes out. So when using hashing, organizations will store, rather than the password, they will store the hash of the password. To authenticate, they will compare the hash of the password just entered to the stored hash on their server. And due to the set output length, hash collisions can occur. So a hash collision is essentially when two passwords have the same hash output. And this can happen, but it's quite rare. Hash passwords are still vulnerable to brute force attacks. And if an attacker can access the database of hash passwords, they can use rainbow tables to work out the passwords. So is there a better way than hashing to store passwords? There is, when we add the salt function, which we'll talk about shortly. So some of the most common hashing algorithms are MD5, which is no longer used for hashing of passwords, but it can still be used to ensure the integrity of data. We have the SHA family of hashes. We have SH1, which is no longer used, the SH2 family, which is now in use, but some of the hash functions from SH2, such as SHA-256 and SHA-512, are vulnerable to length extension attacks. So we now have SHA-3, which is the newest member of secure hash algorithm family, and it's built quite differently to the previous versions. We also have RIPE-MD, which is another family of functions that was developed by the academic community, and it's based off many of the ideas from MD4, which is the predecessor to MD5. RIPE-MD 160 is still considered relatively secure, but hasn't seen widespread adoption. And then we also have Whirlpool, which is a hash function from the square block cipher family, and it's based on a modification of AES, which is one of the encryption standards we looked at. It's considered very secure, but as it's slower than some of the alternatives, it has seen limited adoption. So how does salting help defend against passwords? So salting helps defend against attacks on hash passwords by adding random data to the password before it's passed through the hash function. As salt data is random, even users with the same password will have a different hash. It also helps to prevent hash collisions. Salting greatly increases the amount of time required to brute force passwords using hash or rainbow tables. So let's have a quick look at an example of salting. So if we take the identical password that's there, password 123, and for value 1 we add a random salt, and for value 2 we add a random salt, we can see that those are the inputs for hashing, and when we hash, we get very, very different outputs, and that's due to the addition of the random salt. So the way that a salted password is verified is the salt is stored next to the hashed password. So that way, when the user comes to input his password again, that stored salt is also recalled, and that's added to the plain text password, put through the hashing process, and that's compared with the stored hash. So the salt itself is not a secret. The plain text password with the salt put through the hashing process becomes a stored hash, but we don't actually have to worry about someone seeing the stored salt. So there's a number of common salting algorithms. There's bcrypt, script, argon2, and the advantage of these algorithms is they also add a cost to the function. So the cost is essentially the number of times the hash function is run. So you can see the formula for bcrypt there. It's the password plus the salt, and then the cost. So the number of times that password and salt will be run through the hash function. So as the power of computers increases, the ability of them to run through these algorithms quicker and faster increases as well. So by increasing the cost, we can make these algorithms more secure to more powerful computers. So over 80% of data breaches are due to poor password security. Just looking at a list of common passwords for 2020 in Australia, you can see the most common password is 123456, and you'll find worldwide that's the same. Password is the second most common password. You can see password 1, 123456789, QWERTY, ABC123. So these are the most common passwords in Australia, and unfortunately attackers know that, and they will use that to their advantage when performing password attacks. 50% of people use the same password for all their logins. 57% of people who have been scammed in online phishing attacks still haven't changed their password. And it's very important for organizations to secure the passwords of their users, because 33% of account compromise victims have stopped doing business with companies and websites that leak their credentials. So there's a big financial cost for a company to leak their users' passwords. So how does an attacker attack a password? Well, they can use a number of different brute force attacks. And a brute force attack is when an attacker will try to gain access by trying some way to guess a password. Brute force password attacks in themselves can be time consuming, so attackers will use software and scripts to help them. They can also be quite resource intensive, so they'll use bots or a network of bots to help with the processing. Attackers will also use linked lists of credentials in their brute force attacks, or they'll use hash or rainbow tables sometimes. So brute force attacks can happen in two ways. They can happen online or offline. In an online attack, the attacker is directly interacting with the system that they're attacking. So one way of mitigating online attacks is limiting the number of attempts with incorrect login, and this can help to prevent some brute force attacks. In an offline attack, the attacker has gotten access to a copy of the password database or a list of hashword passwords, and then they can perform a more exhaustive brute force attack on those passwords as it's happening offline, and they're not directly interacting with the system and can't be detected. So we're going to look at a number of different brute force attacks. Let's start with a simple brute force, and that's where an attacker is simply trying to guess manually a password. The next kind is a dictionary attack, and that's where a user will use a dictionary or a word list of commonly used passwords, and they will feed those in and try and guess the password. They often will use software, and the software can account for let's speak. So where the word would be password, again changing letters such as the A to the @ symbol or the O to a 0. For a dictionary attack to be successful, an attacker will often need a large number of attempts against multiple targets. Another kind is a reverse brute force attack. So in a brute force attack, the attacker knows the username is trying to guess the password. In a reverse brute force, the attacker knows the password, and he will use that on a number of different user accounts trying to find the right user account that the password will work with. In a hybrid brute force attack, this is a combination of a simple brute force and a dictionary attack. So essentially, an attacker will take a dictionary of common words, and then they will start to brute force different combinations of numbers and symbols. So that's where we saw this issue with root passwords, for instance, password 01, password 02, password 03, password 01 question mark, password 01 hash, for instance. There's also credential stuffing, and that's where an attacker will get a list of stolen credentials that they've purchased and try that across multiple sites. This plays into the fact that many people will use the same login and password across multiple sites for all of their accounts. And then there's the inverse of that, I guess, which is credential spraying, and that's where a user will use one password against multiple accounts. And this is good for the attacker because it avoids lockout policies. It's using a single password against many, many different accounts, so it's much harder to detect. Lastly, we have rainbow table attacks. Rainbow table attacks aren't actually a password attack. They're an attack against the hash values rather than the password. And here in a rainbow table attack, an attacker will use a table of pre-computed plaintext passwords and their corresponding hashes, and they will look at the hashes that they can access and then compare that to their table to see if they can find the plaintext password. So there's quite a lot of tools out there that attackers can use. I won't talk about all of them. I'll just touch on a few of the more common ones here. So the first one is Cane Enable. Cane Enable is actually a password recovery tool for Windows-based systems. It can perform a number of attacks such as brute force, dictionary attacks, cracking attacks, password hashes, and it even performs network packet sniffing to find passwords. We then have Hashcat. Hashcat is another tool that can be used in password attacks. It can focus on hashes, it can perform dictionary attacks, it can perform combinator attacks, which adds two words together and looks at the hash of the two words together. And then we have the mask attack, where Hashcat will look at the hashes of the most common forms of passwords, which would be a capital letter, 6 letters, and then a number, and try and brute force those passwords. We have John the Ripper, which is another well-known password cracking tool, which performs dictionary attacks, brute force attacks, and there it will allow you to configure the length and position of numbers and symbols Can also perform rainbow table attacks. And then we have Hydra. Hydra is a parallelized network login cracker. It uses a number of different approaches to brute force attacks and works very quickly. The last thing before we finish I wanted to talk about was password managers. So what is a password manager? Essentially, it's a centralized encrypted vault for all of your passwords. Password managers can be device-based or they can be cloud-based. So there's pros and cons to both. In a device-based password manager, all your passwords are securely stored on your computer. They don't go into the cloud. No one else has access to your passwords unless they're on your computer. The downside to that is obviously if something happens to your computer, then you will lose all your password manager, you will lose all of your passwords. The other side of that is the cloud-based, where your passwords are stored by a cloud-based provider. This is obviously the risk that the cloud-based provider also has access to your passwords. So what password managers use, they use this very strong level of encryption, both on device-based and cloud-based password managers. And they will also use zero-knowledge technology, and that means that your passwords are all encrypted on your device before they're sent to the cloud. That means the password managers never have access to your unencrypted passwords. So what's the benefit of using a password manager versus not using a password manager? Obviously, there is a risk, of course, that having all your passwords in one central place for an attacker to access them. But the benefit is that if you use it with very strong levels of encryption, such as AES-256, password managers allow users to use distinct passwords for each of their logins, and it also allows them to use very long and complex passwords, which makes their passwords more secure. So that's why we saw in the latest iteration of the NIST standards that they recommend that password managers are used, which will allow people to use more complex and more or longer passwords than previously. So thank you for watching.